When it comes to machine learning, there are a few common strategies: regression, classification, and clustering. So let's talk about clustering models. First, it's important to note that clustering models are unsupervised machine learning techniques, and that means that we train clustering models without well understood features and labels. The goal of a clustering model is to perform data analysis. In other words, clustering models are primarily used for identifying patterns in your data and therefore learning something about your data. So, for example, imagine we had a parking garage full of vehicles and we wanted to analyze the characteristics of those vehicles so that we could learn something about them holistically. Well, we'd use a clustering model to analyze the data about all of those vehicles, and we could use that information to determine that there's one way to look at those vehicles versus another and to organize in some way. Well, we could use a clustering model to analyze the data about all those vehicles, and we could use that information to determine that one way to look at those vehicles is to organize them by their weight and size. Now, that information then lets us clearly see that there are different types of vehicles altogether: motorcycles, cars, and trucks. Now, we all intuitively understand vehicles already, so we wouldn't need AI to do that for us. But imagine you had some seemingly random data about crowds of people, molecules, or viruses. Well, that's less intuitive, so clustering can help you learn something about your data set through pattern recognition. Now, clustering models analyze data sets and determine which clusters the various data points should belong to. And there are several different types of algorithms that can be used to figure out those clusters. For example, centroid clustering is a mechanism of finding the centers of clusters and then creating equal sized circles from each of those centers and attempting to, quote unquote, capture data points within those circles. Any data point that's inside a circle is considered part of that cluster. Density clustering is similar, except that we work with density clouds instead of circles. That means we try to find obvious groupings of data points. And while clusters can have different numbers of data points in them, density based clusters can also be completely different shapes. Distribution clustering is a mechanism of organizing all the data into certain buckets. So imagine you had a bunch of data between 0 and 100. Now imagine you wanted to put those into three buckets. Well, the first bucket would be all the values between 0 and 33. The second would be the values between 34 and 66. And the last bucket would be the values between 67 and 100. And presto, you've clustered your data. And the last example algorithm is the hierarchy algorithm. Hierarchical algorithms organize the data points based on their relationship to each other. So imagine you're a family tree, for example. If you asked for three clusters from that tree, you'd squish that tree down into certain lineages. The more clusters, the more granular the result. Now, as it relates to clustering, there are a few common models that are generally used. For example, there's the Affinity Propagation model, the K-means model, the Agglomerative model, mean shift, BIRCH, optics, DBSCAN, and the Gaussian Mixture. So let's talk about each of these a little bit. Let's start with the Affinity Propagation model, or AP. With AP, the idea is to look at each of the data points and compare their relative relationship to each other in terms of distance. The advantage of AP is that you don't actually need to know how many clusters to look for at the beginning. It can figure that out for you. Basically, certain data points are nominated as being representative of a cluster, and then all of the data points around them are evaluated from there. So take this image for example. Here we've nominated some data points and then explored the proximity of other data points to arrive at three logical clusters. Next, we have the agglomerative model. This model is a method of organizing data points based on a hierarchical relationship to each other. Take this image for example. Each of the bottom nodes is a data point and technically considered to be its own cluster. But depending on how many clusters we actually want, you'd have to work upwards in the hierarchy to get the proper count. So the agglomerative model creates the hierarchy and then works upwards through the tree to get your clusters. Now it's worth noting that there's a divisive model that is exactly the same, except instead of working upwards through the tree, it works downwards. Another clustering model is the Balanced Iterative Reducing and Clustering Using Hierarchies model, or BIRCH. Again, BIRCH is another hierarchical modeling strategy. It's quite good with large datasets, and it can be modified to use k-means and Gaussian models too. It's very good at handling multidimensional data, and it really only requires a single scan of the dataset to arrive at its conclusion, so it's quick too. Now, in the example image here, we've asked the BIRCH model to create 8 logical clusters of our data. Then, through the hierarchical relationship strategy, the obvious clusters can be determined thanks to the proximity of data points to each other. Next, we have the density-based spatial clustering of applications with noise, or DBSCAN. DBSCAN is a density-based model. It evaluates all the data points in the dataset and tries to determine where the clusters are based on the density of points in a given space. So take this example image. In this scenario, we ask for 3 clusters. Now DBSCAN inspects all the data points and notices some tight clusters. It then tells us which data points are in which cluster. But you'll notice that some of the data points don't land in a cluster. Now, these are considered outlier points or noise. So this can be a good thing if we're trying to eliminate oddball points, but it can also be a bad thing if those points really should be considered. Now, one of the most common models for clustering is k-means. Now, with k-means, we're using a centroid algorithm to identify clusters. Consider this example chart. In this chart, we can very clearly see the clusters even before we apply anything, but that's just to help us visualize. With a centroid algorithm, we try to identify the logical center of certain clusters. Then we expand a circle outwards from that center spot, and the size of the circle is based on the k value that's given by the user. The bigger the circle, the more data points that you theoretically encompass, and the larger the clusters. Now, ideally, there's no overlap between the clusters. So in our example here, we've identified 3 obvious clusters that are each the same size, even if they have a different number of data points. Next, we have the mean shift model. Mean shift is another density-based model. The purpose is to find clusters based on their density. The reason the model is called mean shift is because the circle in which we find data points, as we're seeing on this chart, is moved around to try to find the maximum density. Wherever we find a large density, we call that a cluster. More accurately, in the mean shift model, that's called a convergence. Then there's the ordering points to identify the clustering structure model, or optics. Optics is another density-based model. The main objective of optics, as compared to other density-based models, is to find meaningful clusters. That means that each cluster can have varying sizes, data point counts, or even shapes. Now, take this chart for example. With optics, a cluster is identified based on how data points relate to each other in terms of distance. The first kind of distance is the core distance. This is the minimum distance needed for a data point to be considered core to the cluster. In our chart, that's shown as C. So data points A and B would technically be considered core points. The next kind of distance is the reachability distance. Now, this is a bit harder to explain, but put overly simplistically, the reachability distance is effectively the maximum distance allowed between points outside the core. In our chart, that's shown as R. And finally, we have the Gaussian Mixture model. A Gaussian Mixture model is based on probabilities around the assumption that all data points are generated from a mixture of finite number of distributions. Well, think of a mixture model as a general implementation of the k-means model. So in our example chart, we've once again plotted some of our data points, and then we used the Gaussian model to identify logical clusters based on the centroid strategy that we've talked about before. Now, the important thing to note here is that these clusters can actually overlap, and that means that an individual data point can actually belong to multiple clusters. So, how would someone go about creating and training a clustering model anyway? Well, the first thing you need to do is create or reference a dataset. Data is the lifeblood of any model, so it's imperative that you get yourself a really good high quality dataset. Now, the next thing you need to do is create a pipeline. A pipeline is where all the magic happens. It's where all the steps are defined, configured, and operated against. A pipeline is basically the recipe for your model. Now, in that pipeline, you're going to reference your data, but data isn't always great out of the gate. So you can apply all sorts of transformations to that data to get it to the state that the model trainer requires. Now, once you have your data where it needs to be and you've configured your model training like you want it to, that's when you'd finally execute your pipeline. And that'll actually train your model based on the data that came in. Now, once the pipeline is run, Azure lets you inspect the data that was generated at each step of the pipeline. So you can inspect the input data, the transform data, and of course, the output data. Now, the first thing that you'll need to do when creating a model is create a dataset. It's the most important thing you'll do. The good news is that it's super simple to do that using Azure's ML Studio. Now, with ML Studio, you can just flip over to the Datasets feature and create a reference to your dataset. And there's lots of ways that you can create that reference. You can upload a dataset from a set of files. You can reference a blob storage or some storage account table. You can reference an online dataset. You can even reference an open dataset like weather information. Now, once you have a dataset defined, you can now make that accessible to everyone on your team. Now, that allows people to come in and view the data using the Explore feature in the Datasets view. And as you build pipelines, you can view the data from there too. And speaking of pipelines, that's the next thing that we do once we have a dataset: create a pipeline. So, as I said, pipelines are where the magic happens. A pipeline defines all the steps and the various operations that you'll perform when you set about training a model. Now, to create a pipeline, you'll use a bunch of modules to specify what those operations are. So, that can include data manipulation, custom code modules, testing, scoring, evaluation, and of course, the actual algorithm that you'll use. So, for a clustering pipeline, you'd naturally pick appropriate algorithms like the k-means or Gaussian mixture. Now, in order to train a model or execute a model, you need data, always. So, virtually 100% of the time, the first step in the pipeline is the acquisition of data. The data can be a reference to an open dataset, a reference to a cloud data store, or it can even be manually fed in by a user. Now, wherever it comes from, data is paramount, so it'll always be the first thing that you want to make sure that you have. Which leads quite nicely to the next thing you do. Once you have data, you generally need to consider cleansing that data. Or, to put in more appropriate terms, you need to transform the data. Now, data transformation is used to prepare the data for the processing of model consumption. The idea is that you want to address any issues with the data before it's used. For example, let's say you explore the dataset like I mentioned previously, and while you were browsing the data, you noticed invalid columns, missing data, and wildly different scales of values that you would otherwise consider to be equally important. Well, with data transformation modules, you can take that input dataset, remove undesired columns, remove undesired rows, and normalize certain columns to the same scale to reduce bias during training. There are lots of different transformation modules that you can use. And the worst case scenario is that you can use a custom code module to adjust the input data to exactly the format you require. So it's really quite flexible. Now, once you've got your pipeline to where you want it to be, the next thing you do is actually execute the pipeline. Executing the pipeline means that all the modules are chained together in the pipeline and they'll be executed in the order that you prescribed, and the outputs will be generated based on the provided inputs. So the first thing that's done is that the connected input dataset is retrieved from wherever its source is. Now, once the data is collected, whatever transformation modules were defined are then run in order. So in my previous example, that could be modules that remove unwanted columns, remove or adjust unwanted rows, and finally normalize some important columns to the same scale. Now, once the data is in the state where you need it to be, the rest of the pipeline executes. Now, at that point, you just need to wait for it to run and complete. Now, the rest of the pipeline could be the actual model training, but it doesn't have to be. Sometimes people create pipelines that are just about data cleansing. Then the pipeline becomes the data input to actual training pipelines. Now, that can be very handy if you always have the same batch of transformation operations that you perform before your various model training pipelines. It means that you won't be repeating yourself by always putting the same batch of modules in every single pipeline. Now, regardless, once the pipeline has executed completely, you're now free to explore the results. Now, each module that touches data will give you the flexibility to examine the data it produced. So our input dataset can be explored in its raw state, but then the output of each of the transformation modules can be explored too. So going back to my example, that means that we can see the dataset that's had its columns removed, and that dataset after it's had rows removed, and that dataset after it's had a bunch of its data normalized to some scale. Of course, it also goes without saying that you can, of course, view the output of the trained model, and if you have scoring and evaluation modules, then each of those can have a dataset that can be explored too. How do you explore a dataset? Well, with Azure ML Studio, each module offers you two methods to get to the Data Explorer. First, you can select a module and a panel will appear with the dataset in it, and that dataset includes a button that allows you to click and visualize the data. Or, easier still, you can right-click on the module and select to visualize the data right from there. The visualizer pops up in both instances in a dialog and allows you to see the dataset itself, as well as little histograms for every column of data. And we'll see that a little bit later in the course. In this demo, we're going to create a pipeline in Azure ML Studio to prepare a dataset to be used in a clustering pipeline. To do that, we're going to create a new pipeline through the designer, and then we'll add and configure certain modules to bring in a dataset and cleanse its contents. We'll know it's working if we can execute the pipeline and inspect the data. So first we need to access the ML Studio from our browser. When we create a clustering model, our objective is to analyze data and apply a logical grouping for the data points in that dataset. Basically, we're trying to discover some insights about our data. So the first thing we're going to need is a dataset. So before we get started, let's create a dataset that we can easily wrap our heads around for this exercise. So first, let's head over to the Datasets option. Good. Now let's click on the Create Dataset button and select From Web Files option. So what we're going to do here is we're going to bring in a sample dataset from Microsoft that contains a bunch of information about penguins. In the web URL field, type the following: https://aka.ms/penguin-data. Now let's name our dataset. I'm going to name mine penguin-data. And now we'll click Next. Now we see a preview of the dataset, but we don't want the headers to be seen as an actual row of data, so in the column headers selection, let's choose the Use Headers from First File option. And now we can click Next, and now we can click Next again, and now we can click Create. Good, so we now have a dataset that includes a bunch of information about penguins. So let's park that idea for now. What we really want to do here is we want to author a new pipeline and play around with some modules and how they would connect to each other. So to do that, we need to access the Designer section from the left-hand menu. So let's do that. Now the Designer screen shows us a list of all the pipeline drafts that we already have. In fact, that's what the Designer is doing. It's giving us the ability to manipulate pipelines and how they run. So we want to create our own new pipeline. So to do that, we can simply click on the giant plus button at the top of the screen, and this will bring us to a brand new empty pipeline. So let's do that. Perfect. So now we're in the Designer. We have an empty canvas right in the middle, a list of modules that we can add from the Asset menu on the left-hand side, and some configuration information about the pipeline on the right-hand side. In fact, the right-hand menu is asking us to select a compute target for this pipeline. So let's do that first. We can do that by clicking on the Select Compute Target link. So let's do that. Now in the pop-up, we're asked to select a compute cluster for this pipeline, and that's important. If we run this pipeline, it will add that run to an experiment. And all the experiment runs need to be run using a compute cluster. So with this dialog, we can select an existing compute cluster or even create a new one. To save time, I'm going to select an existing compute cluster that I created earlier and then click Save. And now using the same configuration panel, I'm going to name my pipeline something. You can call your pipeline whatever you want, but I'm going to call my pipeline sbdemo-05-pipeline. And then I'm going to click Save at the top just to be sure. Now we're ready to go. Obviously, what we want to do is we want to build a clustering pipeline, and that means that we want to train a clustering model. But you can't do that without first bringing in some data to evaluate, right? We just created a dataset, so let's use it. To do that, let's open up the Dataset section in the left-hand Assets menu. There's our penguin dataset. Awesome. So let's drag it onto the canvas. Okay, so as I said earlier, this dataset includes a list of a whole bunch of penguins. In fact, let's quickly explore this dataset so that we can see what we're working with. Right-click on the Dataset module and select Visualize Dataset Output. Now in the pop-up, notice that there are 344 rows. Let's remember that for later. 344. The dataset includes all sorts of information about a whole group of penguins. This includes things like flipper length, body mass, species, and so on. This is a pretty decent list of penguins and data. Now you can scroll through this data, but you'll see that some data is missing, some columns might not be needed in a clustering model, and some data is all different scales. Why is that important? Well, the clustering pipeline we're going to want to run is going to try to logically group the penguins. So it's going to try to use all this data to build an algorithm that can do that. If some data is invalid or at different scales than others, then that might introduce bias in the result. So we have to cleanse the data before we can use it. So let's do that. Now first, let's close this pop-up. Okay, so in order to cleanse a dataset, we need to use what's called a transformation. In fact, we're going to use a bunch of transformations. The first transformation we're going to use is the column selector. This transformer will make sure that we're only using the columns that we care about. So in the left-hand menu, let's search for Select Columns in Dataset. Good, and now let's drag it onto the canvas below our dataset. Excellent. Now we need to connect these modules. We want our dataset to flow into the transformer, so drag a connection from the bottom output dot of the dataset to the top input dot of the transformer. Now you notice there's a little warning symbol on the transformer module, and that's because we haven't configured it yet. So let's click on the module to make sure it's selected, and mine is. And in the right-hand panel, click on the Edit Column link. Now this pop-up is asking us to choose which columns it should care about. In actuality, we care about all the columns except for one. So let's click on the By Name Radio button. And now this is listing all the columns in the dataset. Now we want all the columns except the species column. That column represents way too much bias for our clustering model to accept, so we're going to ignore it. So let's first click on the Add All link at the top of the available columns list. Now let's remove the species column from the selected columns list by clicking on the little minus sign beside its name. Now we can click Save. So what we've done is we've taken an input dataset and removed a column from it because it represented too much bias opportunity. Meanwhile, the remaining columns are known to maybe have some missing data. So what we want to do now is add another transformer that decides what to do when it encounters missing data. To do that, let's find the Clean Missing Data module in the left-hand list and drag it onto our canvas. Now we'll connect the output of our existing transformer to the input of our new transformer. And once again, we see a warning symbol because we haven't configured the new transformer. So let's select the module, which I have, and click on the Edit Column link on the right-hand pane. Now, in this case, there aren't many columns, and we want to handle cases where any of them are missing data. So let's leave the With Rules Radio button selected. Now, in the Include field, let's select the All Columns option. Now we can click Save. Now with the columns selected, we can now apply the rules of what to do when missing data is found in them. What we're going to do is we're actually going to remove the entire row from the dataset if missing data is found in any of these columns. So let's choose the Remove Entire Row option from the Cleaning Mode field. So we now have a regular dataset that flows into a transformer that removes undesired columns, and then flows into another transformer that removes undesired rows. That means that our dataset now only has the data that we care about. But now we want to transform the data itself. Remember how I said that some of the data had totally different scales? Well, if some data has huge numbers and some has really small numbers, a model might apply some unfair bias to the bigger numbers because they sway so much more than the smaller ones. You know that these values are of equal importance, so what we want to do is we want to equalize them, or more accurately, we want to normalize them. To do that, let's find the Normalized Data module in the left-hand panel and drag it onto the canvas. Now let's connect the left output of the missing data module and connect it to the input dot of our normalizer. And once again, we're seeing a warning symbol, so let's click on the new module, which I have, and then click on the Edit Column link once again. Now once again, let's select to include all of the columns in the normalization step. What we're doing here is we're saying that all the columns are of equal importance. Anyway, now let's click Save. And now let's change the transformation method at the top of the panel to min-max. So at this point, we've created a dataset, added it to a pipeline, and now we've cleansed it using a few transformers. So let's see it in action before we start using it in our eventual clustering model. Let's click on the Submit button at the top of the page. Now in the pop-up, it's asking us to connect our pipeline run to an experiment. Well, since we don't have any experiments yet, let's create one. Let's click on the Create New Radio button. And let's give our experiment a name. I'm going to name mine SBDemo-05-experiment. Now let's click Submit at the bottom of the pop-up. Now this kicks off the model run, and it might take a while to run. So I'm going to fast forward to the end. Fantastic! Now that our pipeline run is complete, you can see all the modules have been highlighted with a green bar and the word completed. So let's prove it. Right-click on the Normalized Data module and select Visualize Transformed Dataset. Now right away notice that we only have 342 rows versus the original 344. The species column is gone, and the columns that we do have are all in the shared range between 0 and 1. So that's it. We've created and prepared a dataset, and we're all ready to run a clustering pipeline. In this demo, we're going to build and execute a clustering model training pipeline. To do that, we're going to piggyback off our last demo where we prepared a dataset. The purpose of our model will be to try to figure out some sort of logical grouping for a dataset of penguins based on their various characteristics. Okay, so the first thing we need to do is open the Azure ML Studio in our browser. Alright, now in our last demo, we created a pipeline, so let's open it back up. To do that, click on the Designer item in the left-hand menu. Now on the bottom section of the page, find your pipeline and click on it. Mine was SBDemo-05 pipeline. Now let's do a quick recap of what this pipeline is doing. So far, we've got a few modules on the pipeline canvas. The top module brings in a sample dataset from Microsoft that includes a bunch of data about penguins. The other modules that are connected to the dataset after that help to remove unwanted columns and unwanted rows, and then normalize a set of columns in order to bring them to a more equal scale so that we can avoid any unnecessary bias when it comes to feeding it into a model trainer. And that brings us to the task at hand. What we want to do in this demo is create a clustering model trainer that's able to logically group our penguins into a set of groups that make sense. The eventual objective would be to pass in some data into an already trained model and have it group a new set of penguins into those same types of groups. Well, to do that, you need to first train a model with some existing data. Now, our dataset doesn't have the answers in it, so this is unsupervised machine learning. So what our model will attempt to do is learn from the data and then try to create an internal algorithm that logically groups the penguins based on the data that it seems to suggest. So let's do this. The first thing we need to do is actually something to help us test the model in the end. So the first thing we want to do is add a split data module. So find that module in the left-hand panel and drag it beneath our current stack of modules. Now let's drag the left output of the normalize module to the input of the split data module. Now what this module does is it takes some of the input dataset and splits it into two sub-datasets. Why? What we want to do is we want to feed some of the data into our model training and then the rest of it into another module that'll help us score how we did. But how much should we send? Well, let's click on the module to make sure that it's selected, and mine is. And now in the right-hand panel, we can choose what the split will be and how it gets split. So let's set the fraction to 0.7. Now what this means is that 70% of the data will go to the first output and 30% will go to the second output. Let's also set a random seed value so it doesn't just start at the beginning. Let's set the random seed field to 1, 2, 3. Now we're ready to train a model. So let's go back to the left-hand panel and find the Train Clustering Model module, and then drag it onto the canvas below our Split Data module, but slightly to the left. Now let's connect the left output of the Split Data module to the right input of the Train Model module. Now what this does is feed in 70% of our dataset into the dataset input of the model trainer. Now you notice that there's a little warning icon on our new module, and that's because it's not totally set up yet. So let's click on the new module to make sure it's selected, and mine is. And in the right-hand panel, let's click on the Edit Column link. Now remember that what we want is for the model trainer to logically group our penguins based on whatever data is in the dataset. So we need to tell it to do that. So in the Include field, let's select the All Columns option and then click Save. We're now set up to logically group our penguins, right? Well, not exactly. You see, what we've done here is we've told the model trainer what to do, but we haven't told it how to do it. To do that, you need an algorithm. Now, clustering models are great for finding some sort of mechanism of grouping data from the input dataset, and there are lots of algorithms that you can use. But for our purposes, we'll use the most common algorithm. Let's use the k-means algorithm. Now back in the left-hand panel, find the k-means clustering module. And let's drag it onto the canvas above our model trainer. Now let's connect the output of the new module to the left input of our model trainer. Now what this module will do is cluster our data based on the k-means strategy. All we have to do is tell it how many clusters we want, so let's tell it. Let's set the number of centroids option to 3. Now we've got a clustering pipeline that groups our penguins into 3 logical groups. Fantastic! Well, to know the answer to that, we've got to explore our output, don't we? So let's do that. Search for the Assign Data to Clusters module and drag it onto the canvas below our model trainer. Now let's connect the model trainer output to the left input of our new module. So how does this new module work? Well, the module takes the trained model from our model trainer and applies it to another dataset. The input dataset is then clustered according to the rules derived by our model trainer. Well, remember our split data module? Well, now we can connect the right output of that module to the right input of our new module. And that means we're going to attempt to cluster the remaining 30% of our cleansed dataset based on the rules from our trained model. So let's connect them. Now at this point, we've got a pipeline that uses a clustering algorithm to train a model to logically group penguins based on a cleansed dataset. We then take that trained model candidate and run it against part of our dataset that wasn't used to train the model and cluster that data with our trained model. So let's run this and see what we get. Let's click on the Submit button at the top of the page. Now in our last demo, we created an experiment. Let's use the same experiment this time. Choose the experiment you used last time in the existing experiment field and click Submit. Now our pipeline is executing, and that process can take some time, so I'm just going to fast forward to the end of the run. Now our pipeline is finished executing, so let's make sure the Assign Data to Clusters module is selected, and mine is, and notice that there's an Outputs and Logs tab in the right-hand panel, so make sure that that's selected too. Now right at the top in the Data Outputs section, there's now a Results Dataset object. On that object there's a Visualize icon. So let's click on that so that we can see the results of the data clustering. Now in the pop-up, notice that there's now an Assignments column with either the number 0, 1, or 2 in it. That's our determination of which cluster each penguin should be in. If you scroll through the list, you should see each penguin in a particular cluster. Now you can analyze the data and figure out why the model decided each penguin should be in each group, and that can give you some insights into your data. In this demo, we're going to add an evaluation module to a clustering pipeline in Azure ML Studio so that we can evaluate the results of a candidate model. We'll see how to add and configure the module in the pipeline canvas. Finally, we'll execute the pipeline and explore the results of the evaluation module. Okay, so the first thing we need to do is navigate to the Azure ML Studio using our browser. So in this demo, we're going to piggyback off our previous demo where we created a clustering pipeline that trained a model on how to logically group a dataset of penguins based on their characteristics. So let's open that pipeline. Click on the Designer option in the left-hand menu. Now let's select our pipeline from the list at the bottom of the page. Mine was called SBDemo05 Pipeline. Now we're presented with the designer. On the canvas, we've already got a set of modules that do a bunch of things. First, we have a dataset that we created based on some sample data from Microsoft that includes a bunch of information about penguins. Then we run that dataset through a set of transformers to remove columns, remove some rows, and to bring the remaining data to the same usable scale so that we don't introduce bias into the model training. And speaking of model training, after the data cleansing, we feed 70% of the dataset into a model trainer, which is set up with a k-means clustering algorithm, and the other 30% goes to a module that uses our candidate model to be clustered. So with what we built before, we can easily check to see how or if our penguins were clustered. We do that with the Assign Data to Clusters module at the bottom of the pipeline. But in this demo, we're going to evaluate the results of our clustering. Just eyeballing the clusters doesn't really tell us if it was effective or not. Now, configuring a pipeline to evaluate a candidate model is pretty easy actually. So let's go over to the left-hand panel and search for the Evaluate Model module and drag it onto the canvas below our Score Model module. Now let's connect the output from the Assign Data Clusters module to the left input of our new module. Now that's it. Let's run the pipeline by clicking on the Submit button at the top of the page. Now, in our last couple of demos, we attached our pipeline to a particular experiment. So let's do that again. Let's select the same experiment we've been using. For me, I'll choose the SBDemo05 experiment. Then we'll click Submit. Okay, so as usual, the pipeline may take a while to execute, so I'm going to fast forward to when it finishes. Perfect! Our model has executed successfully. Now let's explore the evaluation results. Click on the Evaluate Model if it's not already selected, and select the Outputs and Logs tab. Now notice that there's an Evaluation Results dataset at the top of the tab, so let's click on the Visualize icon to explore the results. Now, we're seeing a number of statistics in this pop-up. First, we have the average distance to other center. This particular metric tells us how close, on average, each penguin in a given cluster is to the centroids of all the other clusters. This helps to tell us how much potential overlap there is between penguins being in their current cluster versus being in another cluster. Basically, this helps tell us if our clusters make sense. Next, we have the average distance to cluster center. This metric tells us how close, again on average, each penguin is to the centroid of its own cluster. And this helps to tell us how good our clusters really are. If the average distance to other clusters is close, but this stat is really close, then it implies that our data might be really dense. Another metric is the number of points. This is pretty straightforward. This is telling us the number of penguins we have in each cluster. Ideally, they're about the same because it implies even distribution, but it doesn't have to be. For example, if you determined a logical grouping of vehicles in a parking garage is their type, then you might have a really small cluster of motorcycles and a huge cluster of cars. That doesn't make the grouping wrong. And finally, we have the maximal distance to cluster center. This metric tells us the maximum of the distances between each point and the centroid of that point's cluster. This metric helps us to figure out how spread out a particular cluster is. If the metric is high, then the cluster would be considered to be widely dispersed. If it's low, then the cluster is pretty tightly packed. So in this case, we can take a look at our metrics, and now we can make a more educated decision on how good our candidate model is at clustering our penguins. Looking at this data, we can decide if our model clusters are in a way that we like them. If it doesn't do a good enough job, we can spend time to make the predictions even better by transforming our data set some more, or even just adding some more data. I mean, remember, we only had 342 rows. On the other hand, if we like our results, then we can go ahead and deploy our model. Regardless, we successfully run a clustering model and we've successfully evaluated it. In this demo, we're going to create an inference pipeline in Azure ML Studio. To do that, we're going to piggyback off our last few demos and use an existing clustering pipeline that logically groups penguins into clusters based on their characteristics. First, we need to navigate to the Azure ML Studio in our browser. So in this demo, we're going to piggyback off our previous demos where we created a clustering pipeline that trained a model on how to logically group penguins based on a bunch of their characteristics. So let's open that pipeline. Click on the Designer option on the left-hand menu. And now let's select our pipeline from the list at the bottom of the page. Mine was called SBDemo05 Pipeline. So here we are once again presented with our clustering pipeline. So let's do a quick recap of what's going on here. First, the pipeline takes a dataset that includes some sample data from Microsoft. That dataset contains a bunch of information about a bunch of different penguins. We then use a set of transformation modules to remove unwanted columns, remove unwanted rows with missing data, and then normalize the remaining data to make sure that they're all using the same scale, which then prevents any introduction of bias in the model. We then feed 70% of our cleansed dataset into a model trainer, and the remaining 30% goes to our now trained model for clustering. Now what we want to do in this demo is be able to feed in new datasets against the model we just trained. To do that, we need to create what's called an inference pipeline. So let's go ahead and get that ball rolling. Now to create an inference pipeline, we need to click on the Create Inference Pipeline button at the top of the screen. Now in the drop-down, there's a couple of options. For us, we want to be able to test datasets on a sort of ad hoc basis. So we're going to choose the Real-Time Inference Pipeline option. So let's pick that option. So now what we've got is a whole new pipeline. It's worth noting that this is pretty much the same pipeline we already had, but with a few differences. First, you'll notice at the top of the canvas that there's a web service input module, and that's been placed right beside the dataset module, and they both feed into the next module. This means that this pipeline can now be triggered by a dataset sent in via web service endpoint. Pretty fancy, and we'll get to that later. Next, we'll see that there's a couple of apply transformation modules. This is just a different way to represent our various transformation steps. Next up, we get to the Assign Data to Clusters module. This takes our trained model and applies it to whatever dataset was provided. And finally, the pipeline outputs the results to two modules. One is our evaluation module so that we can explore the results later on, and the other is the web service output module so that we can return information to the consumer. And that all sounds pretty wild, right? Well, I'm going to make a few modifications to this pipeline to make our lives even easier. First, I'm going to rename the pipeline so that it matches my existing pipeline a bit closer. I'm going to call the pipeline SBDemo05 Pipeline Inference, and I can do that by using the little cog icon beside the pipeline name and then typing the name in the configuration panel. And I'm also going to confirm the compute target is configured properly, which it is. Next, I'm going to remove the original dataset. Now that dataset that we used in our original pipeline was used to train a model, but it won't be needed when it comes to actually running in the future with real data. So let's select the module and click Delete. Now what I do want is the ability to run this manually and be able to provide data on the fly. To do that, I want to add a module for manual data entry. So let's search for the Enter Data Manually module and drag it onto the canvas where the original dataset was. And now let's connect it to the Select Columns and Dataset module. Now you notice that there's a warning symbol on this module, and that's because the module hasn't been fully configured yet. So let's do that. Let's make sure that it's selected so that we can see its configuration in the right-hand panel. Now I'm going to copy and paste some CSV data into the data box here. Don't worry, I'll include it in the doobly-doo so that you can use the same thing. Now it's worth noting that in this dataset that I've just provided, there's no species column like there was in our original sample data. Now the next thing we want to do is remove the evaluate model module. When this pipeline is run by consumers, they'll have no real access or need for the evaluation module. It's not really needed in this pipeline then, is it? So let's select it and delete it. Perfect. So now we have a pipeline that takes data from a web service input or manually, does the usual cleansing, and then applies our model. The output of the model run is then output back to whichever web service initiated the request. So let's try it. Let's click the Submit button at the top of the page. Now the pop-up is asking us for an experiment. Now in this case, we're going to put this into a new experiment. So let's click on the Create New Radio button. And let's give our experiment a name. I'm going to call mine sbdemo-05-experiment-inference. Good. Now let's click Submit at the bottom of the pop-up. Okay, so as usual, the pipeline may take a while to execute, so I'm going to fast forward to when it finishes. Our run executed, so let's look at the results. We can do that by looking at the output of the Assign Data to Clusters module. So let's click on it to select it. And now let's go over to the Outputs tab, and mine's already selected. And now let's view the dataset it created. Awesome. So now we see a very familiar looking output dataset that has the columns we expect. It only has 3 rows, 1 for each input row, and it shows which cluster the penguin was added to. In this demo, we're going to deploy a predictive service using Azure ML Studio. To do that, we're going to piggyback off our last few demos and use a built-in deployment mechanism against our existing inference pipeline to create a new endpoint. We'll know our deployment is working if we can access the results externally using Postman. First, we need to navigate to the Azure Machine Learning Studio in our browser. So in this demo, we're going to piggyback off our previous demo where we created an inference pipeline based on our clustering pipeline training that we did in demos previous to that. This inference pipeline allows us to logically group penguins based on a bunch of their characteristics. So let's open the inference pipeline. Click on the Designer option in the left-hand menu. Now let's select our inference pipeline from the list at the bottom of the page. Mine was called sbdemo-05 Pipeline Inference. Good, so here we are once again presented with our clustering pipeline, so let's do one last recap of what we did here. First, the pipeline takes a dataset as its input. Then that can be manual or from a web endpoint, and more on that later. The dataset is expected to contain a bunch of information about penguins. We then use a set of transformer modules to remove unwanted rows and then normalize the remaining data to something we can use. The data eventually flows through another set of modules that actually runs the data against our model, and the output from that model run is then sent out to a web endpoint. Now the whole point of this inference pipeline is to be able to place penguins into appropriate logical clusters based on the characteristics or features that made sense during the model training. In other words, if a scientist inputs a bunch of relevant information about a penguin into our pipeline, then our model should be able to tell the scientist which cluster the penguin belongs to. So if we want a user to be able to access our pipeline, the first thing that we need to do is deploy it. So let's go ahead and do that. On the top right of the screen is a deploy button right next to the submit button. So let's click on that. Now deploying a pipeline means creating an endpoint. An endpoint is a URL that can be used to specifically access your pipeline. So the pop-up dialog here is asking us for details about how we want to configure our endpoint. The pop-up wants us to give a name to our endpoint, so let's do that. I'm going to call mine sbdemo-05 endpoint. Next is a description. This can be useful for Swagger information, and I would generally recommend setting this value, but in this case I'm going to leave that blank. And lastly, we have the compute type selection. Now because this is an inference pipeline, we can technically use a Kubernetes service to run our endpoint. So if we leave this selection as it is, then we're asked to choose a Kubernetes cluster to use. In my case, I don't have a Kubernetes cluster, so instead I'm going to select Azure Container Instance. Now our endpoint is ready to be created, so let's go ahead and click Deploy at the bottom of the screen. Now the endpoint creation process may take a moment, so I'm going to fast forward a bit here. Now at this point our endpoint exists. Well, let's prove it. To do that, we're going to use Postman to submit a new dataset to our deployed endpoint and see what it tells us. Now in order to do that, we'll need some information about our endpoint. So let's click on the Endpoints item in the left-hand menu. Now let's find our new endpoint and click on it to access its details. Now when a consumer wants to talk to an endpoint, they require two bits of information, the URL and a key. And both of those bits of information can be found in the Consume tab, so let's click on that. So what we need from this screen is the REST endpoint value and one of the two keys at the bottom of the page. So let's copy those over to Notepad. So now what we want to do is actually interact with our pipeline via this endpoint. To do that, we're going to open up Postman. Now if you don't have Postman, you can get it for free at postman.com. Now Postman provides an interface for interacting with any web endpoint. So what I'm going to do here is bring in a request that I've already prepared, but don't worry, I'll provide that request in the doobly-doo so that you can copy it too. First, I'm going to select to import a file using the Import button at the top of the screen. Now I'm going to browse for my file by clicking on the Upload Files button in the middle of the pop-up. It recognizes the file. Now let's click the Import button at the bottom of the pop-up. Now what we need to do is configure this request with a couple of bits of information that it needs. Now first, you'll notice that this is a POST request, but it's missing the actual endpoint URL. So let's replace the part that says Your Endpoint with the endpoint URL we copied over to Notepad. Now let's click on the Headers tab below the request URL. Notice that there's an authorization header. In that header, the value includes a piece of text called Your Key. So let's replace that value with the key that we copied to Notepad. Now before we do anything else, let's quickly take a look at the body of this request. We can do that by clicking on the Body tab below the request URL. The body is where we're defining the input dataset. Now pay special attention to that dataset. Notice how there's an inputs object that contains an array called Web Service Input 0. If we were to inspect our inference pipeline, we'd notice that this is the exact name of our Web Service Input module from our pipeline. And this is important. If we called that array anything else, it wouldn't work. Meanwhile, inside that array is a single object with fields and values. And this object is clearly defining a penguin. The fields match the dataset that's expected as the input dataset. If they didn't match, there'd likely be issues, or maybe the model wouldn't provide any results because the row would be removed entirely. Now, this is a demo after all. Real code would protect against bad input. Alright, so let's go ahead and execute the request and see what happens. We can do that by clicking the Send button on the top right of Postman. Excellent! We got a result back. Now let's take a look at that result. Notice that the result object contains a results subobject that itself contains an object called Web Service Output 0. And if you inspected our inference pipeline again, you'd notice that that's the exact name of our Web Service Output module from our pipeline. And also notice that the values that are returned are now including which cluster the penguin belongs to in the assignments field. Amazing! So now we have a clustering pipeline that trained a model to logically group penguins into clusters based on their characteristics. We deployed that model, and then we created a Postman request to access that deployment. In our request, we passed in information about a penguin, and our model told us which group or cluster that penguin belonged to. So in this course, we've examined Azure machine learning clustering models. We did this by exploring available types of machine learning clustering models, clustering model training and concepts, k-means clustering model in Azure Machine Learning Studio, evaluating a clustering model and creating a clustering model inference pipeline, and deploying a clustering model-based inference pipeline. Now, in our next course, we'll move on to examine Project Jupyter and its use for machine learning.